So we're going to start chapter 5, which is auxiliary functions. Auxiliary functions are namely the internal energy, the enthalpy, Helmholtz free energy, and Gibbs free energy. These four energy terms. So basically, we'll go through the relations between all these four and their dependence on, for instance, volume, pressure, temperature, entropy. So we'll see like the correlation between dependent variables and independent variables. So basically, these are all, most of them are just math. So in chapter 5, especially for the problem sets, you'll see a lot of math problems. They are not really related to thermodynamics calculations, but they are mainly math problems. So basically, for energy conservation, we already know that the change of heat, the change of heat is the change of internal energy of the system, and the change of work, or the work done by the system. That is from the first law. And from the second law, we also know that the change of the entropy for the system is the heat absorbed divided by temperature, but there is an irreversibility term if the process is an irreversible process. So if you're dealing with reversible process, then you don't have this second term on the right-hand side. But if you're dealing with an irreversible process or regular process, then you have to take that into account. So that's the reason why if you combine these two equations together, you'll end up with this. And the reason why you have this inequality here is because we typically cannot know how large this delta S IRR is. So it means that the DS system is, I think we've already went through this several times. You can say this is greater than this. Therefore, if you combine these two, you'll see that the change of work is actually less than TDS system minus DU of the system. Okay? And we actually already saw this before, because if you consider the temperature is a constant, and since the entropy and the internal energies are both state functions, so consider a process evolving from state A to state B, then the difference of the entropy will be the final entropy minus the initial entropy. And that will be the same for internal energy. So if you write this down, we've already seen this before, that the work should be no greater than this value. If you consider any kinds of process, the maximum work that a system can do will not surpass this. And if you still remember, when I mentioned this before the midterm exam, I called A defined as U minus TS as the Helmholtz free energy. And if you have this term, then you realize that this is the maximum work that a system can do is actually the difference of Helmholtz free energy before and after this process. So this is a measure of how much work the system can do if you are trying to figure out the work done by the system for any kinds of processes. So of course, if you're going through a reversible process, then you can get the maximum work. So the work will be equal to T delta S minus delta U. Okay, that's the case when you're going through a reversible process. So thermodynamics methods provide equilibrium criteria, determine the influence of changes in the external influences. But the practical usefulness of thermodynamics method largely relies on the practical practicality of the equation of states of the system. So, which means that the relationships which can be established among thermodynamic properties of the system. So these are a lot of words. And the bottom line is that you have to know like what, for instance, internal energy before and after the processes and the entropy before and after the processes to calculate the maximum work, right? Because in this equation, if you want to use Helmholtz free energy, you need to know the internal energy and the entropy, and then such that you can calculate the difference and then estimate the maximum work. So there are a lot of factors that you have to consider in order to determine that quantity. And so by combining the first and second law that we just saw, we end up with this equation, du is TdS minus PdV. And this is when the case is a closed system and the composition is also fixed and you don't have any work other than the PdV work. So we know that if you went through the textbook and you know that there are several different kinds of work other than the PdV work. This PdV work mainly is for instance, gas system. You have pressure and then you expand the volume, then the system is doing some work to the outside. However, if you're dealing with, for instance, a magnetic system, you know that by applying magnetic field and the magnetic moments will align with respect to that magnetic field. Therefore, you're also doing some work. And I think in the textbook, it mentions that there are some other kinds of work, for instance, in the, like the magnetic work. So if you're dealing with a system that is not just involving the PdV work, then you have to take all those other terms into account. But in this case, the simplest case, you only need to take into account the PdV work. So the work done here is the volume change against the external pressure, which is the simplest form. And the criterion for equilibrium from the first law and the second law combined will be for constant U and V, then the entropy will go to maximum. And if you're dealing with constant entropy and constant volume, then the internal energy should go to its minimum. So actually, we've already mentioned this last time as well. And it can be just from the equation, because if you fix internal energy and the volume, which means that these two terms are fixed, then we know that ds should go to 0, right? If your du and dv is 0, then the ds should also be 0 to satisfy this equation. So ds is 0, it means that s should reach some extreme value. And in the case of second law of thermodynamics, we know that entropy should go to its maximum. And for the other case, constant s and u, which means that ds is 0 and dv is 0, then du should also be 0, right? So in that case, there are two possibilities. The internal energy goes to its maximum or goes to its minimum. And we know that naturally, this should go to minimum because it will minimize the internal energy and reach an equilibrium state. So these are just the examples of how you look at this equation. So once you have this kind of equation written down, then you know that if you have two constraints like ds and dv, then you can constrain this term as well. Okay, for instance, in this case, if u and v are fixed, then s should be fixed when the system reaches equilibrium. And for the case of s and v is fixed, then u should go to its minimum. So this is just an example of using what we already learned just by using the first law. And internal energy, like I mentioned, is actually the first auxiliary function that we will use. So in this chapter, we will see there are four different I would say, auxiliary functions. Internal energy, we already mentioned this, and also the enthalpy, and Helmholtz free energy, and the Gibbs free energy. Okay, so we have four thermodynamic quantities that can allow us to do some math tricks. So there are a lot of words. So again, the first note is what I just mentioned, because if you're dealing with a system with some other kinds of works, for instance, magnetic work or electric work, then you need to add some other terms, or chemical works. But if you're just dealing with PV system, for instance, gas system, the only work done by the system will be PDV, then you can use the equation that we just saw. However, if you're dealing with other system, I think if you read the textbook in chapter 5, you'll see that in some cases they will add a magnetic term. And I won't mention that in class because that's sort of beyond our scope. And if you're using the last version of your textbook, then you don't have this kind of problem. But I don't know why in this version the author tried to add this in. But for simplicity, I will ignore the magnetic work and electric work that will be in your new version of the textbook. But the bottom line is that in the case that we just saw, we ignore the works other than PV work. And since entropy can neither simply measure nor simply control, so there are a lot of equations that's involving entropy. For instance, we know that if we write du as TdS minus PDV, it means that we express internal energy as a function of S and V. But in reality, it is really hard to measure entropy. You can measure volume easily because that's the thing that you can control. But it will be really hard for you to measure the absolute value of entropy of the system. So in that case, this expression might not be a very good expression. So if you can express internal energy as a function of, for instance, temperature and volume, then it should be a better expression for us to do experiments. So the second bullet point here is that since entropy can neither simply measure nor simply control, so the set S and V is an inconvenient choice of independent variables. So again, typically we express these auxiliary functions or thermodynamic quantities as a function of two independent variables. So in this case, if you follow the first law and the second law, you'll end up with internal energy as a function of entropy and volume. But as I mentioned, these two variables are not very useful because volume can be fixed, but entropy is hard to control. So it means that we have to figure out some other ways to express internal energy. So the third point is that other than equation 5.1, this one, a similar equation must be derived, providing a more convenient choice, like I just mentioned. What you should do is do some mathematical tricks to change this thing, like ds, into some other stuff, such that you can do other calculations. Because using this, you'll find it really hard to do anything. So practically, like I mentioned, pressure and temperature are the most convenient variables. So if you do a lot of experiments, you'll realize that a lot of these kind of measurements involve the measurement of pressure and temperature. So it seems that these are the most convenient variables. And more importantly, these variables these two are intensive. Which means that they don't depend on the size of the system. If you still remember during the midterm exam, I asked you what are intensive variables, what are extensive terms. And since pressure and temperature are both intensive, it means that once you measure that, those things are independent of the size of the system. Okay? So those are much easier to be measured. If you're trying to measure, for instance, entropy, we know that this is a size-dependent variable. So it really depends on how many, for instance, particles that you can measure. But P and T are both the macroscopic quantities that as long as you have a thermometer, you have a pressure gauge, then you can get those two numbers. And one number for pressure, one number for temperature, and you can tell a lot of stories. So in reality, we want to change these things into, for instance, pressure and temperature. And therefore, we need some mathematical tricks to help us do that. And for statistical approach, you will use different variables. For instance, volume and temperature. Actually, we saw this earlier when we tried to derive, for instance, I think the entropy of the ideal gas. We use as a function of, for instance, U and V and T. Sorry. Okay. So volume and temperature are also favored when you're dealing with statistical mechanics. And why volume is important is because when we're dealing with statistical mechanics, we're typically working on microscopic systems. And when we're dealing with microscopic systems, again, we're using those quantum mechanics, and therefore we need to have quantized energy levels to be fixed in order to discuss. And if you still remember in chapter 4, we mentioned that constant volume is important for us to discuss fixed quantized level because those energy level differences, for instance, for a quantized system, you have different energy levels. Let's say from ground state. And the difference, let's say delta epsilon, will depend on volume. So if you change the volume of the system, then it means that the energy level will be changed. Okay? So for a larger system, typically the delta epsilon or delta E will be smaller. That's the reason why for microscopic systems, for larger size systems, typically you cannot see any quantization of energy. Only when you go down to microscopic systems, for instance, nanoscale or micron scale, you can start to see the quantization of energy levels. So therefore, for when you're dealing with statistical mechanics, fixed volume and fixed temperature, or controlling volume and controlling temperature will be a better choice or better combination of choice. So know that this is the reason why we need to have constant volume. It's because the quantization of the energy levels. And together with constant T, once you have constant T, you know that the Boltzmann factor will be fixed. Because the distribution of particles among these energy levels will follow this exponential law. This is the Boltzmann factor. And the KBD will be fixed if you have a fixed temperature. Therefore, you'll see that distribution of the particles will be fixed. So this is this discretization is related to volume, and this distribution is let's see, is related to temperature. Okay, so that's the reason why for a statistical approach, typically we want to have fixed temperature and fixed volume, such that we can fix the system and allow us to do the discussion much easier. So the auxiliary thermodynamic functions have dependent variables that are related in simple form to more convenient choices of independent variables. So which means that if you're dealing with a system or a problem that's giving you entropy and volume, then of course you don't have to do anything. You can just use these two independent variables to discuss this dependent variable. However, if you're dealing with other other independent variables, for instance, the problem tells you now we can control pressure and temperature, then you cannot use this one, right? Because these are not P and T. So you have to do some mathematical tricks or see if this one can use P and T or either this one. So later we'll see that for all these four, they all have like different dependence on those independent variables. Okay, and there are some already derived thermodynamic expressions. I think we've seen this before when we talk about this expression We've already derived that temperature is partial U partial S with fixed volume, and the pressure is partial U partial V with fixed entropy. Those are directly from here, right, from this one. And of course, partial S partial V with fixed internal energy is P over T. This can be derived by using these two. Okay. So in short, actually we can write this down just to summarize this section. So if you start from the first law, so we have this so we know that this means that internal energy is a function of S and V. And we also know that this means something like this, right? So if this is a perfect differential, we can express this like that. And therefore, you have the relation like T is, and the pressure is minus. So these are fairly simple. So the problem is, are these expressions really useful or not? For instance, if we measure temperature, then it means that if we fix the volume, the temperature actually tells us the rate of change between internal energy and the entropy. Okay, but since we don't know how to measure entropy, this seems to be pretty useless. Okay, this one may be more useful, but that's the case when we know how to express internal energy. Then if you measure pressure, and if you can measure the change of pressure as a function of a volume, then perhaps you can express internal energy of your system. So it really depends on what are the variables involved in these expressions. Okay, and we'll use these to do some mathematical tricks to help us replace those things into the variables that we want. And enthalpy is pretty straightforward, so I guess we don't have to spend a lot of time on this. We've already seen this in the very first two chapters, that the enthalpy can be defined as U plus PV. And so if you're dealing with a closed system and it's undergoing a change of state at constant pressure, this is fairly important, at constant pressure. Although the definition of enthalpy, I emphasized this several times, is not limited to constant P processes, but typically when we use enthalpy as our measure of change of heat, we're dealing with constant pressure processes. Okay, and so if we're dealing with constant pressure process, then the change of internal energy is the heat minus the change of work. If you use this expression, then U plus PV will be a good measure of the change of heat, right? So delta H, or H2 over minus H1 is just the heat absorbed by the system. So the change in enthalpy equals the heat entering or leaving the system when you are dealing with constant pressure process. So it means that when you're dealing with enthalpy, you know that it is when people tell you your P is constant, right? So when the problem states that you're dealing with an isobaric process, typically if you want to calculate heat, you need to use enthalpy. And we've already discussed this before. But more importantly, the new term that we want to introduce is the Helmholtz free energy. And we've already, actually I just erased that, but we've already mentioned this before when we discussed the maximum work the system can do. And so if you define the Helmholtz free energy as U minus Ts, Again, this is very similar to the definition of enthalpy. It's U plus PV, but it doesn't state, it's not necessary that this term should be used in, for instance, constant pressure or constant temperature processes. But when we want to discuss Helmholtz free energy, typically we want to state that the system is undergoing an isothermal process, which means that the temperature is constant. Okay? So if we're dealing with a constant temperature process or isothermal process, it means that the change of Helmholtz free energy is Q minus W minus T delta S. Okay? So from the second law, we also know that delta S is no less than or greater than, should be greater than Q over T. Therefore, if you replace these things into this formula or this expression, you'll see that you'll retrieve this term. So the change of Helmholtz free energy represent the maximum work that the system can do. Okay, or if you change the sign, so A1 minus A2 will be the maximum work the system can do. So the reason why you have a minus sign here is because here you have a minus sign, and this is the final minus the initial. So we know that if you plot this out, so originally A1 is here, and let's say A2 is here. And this is evolution from state 1 to state 2, and this difference is no greater than W. Okay? Or let's say this is the maximum work the system can do will be the difference between Helmholtz free energy. And this is when the system is having a constant temperature constraint. Okay, so that's different from what we just learned earlier, or what we just saw earlier for the enthalpy. For the enthalpy, the constraint will be constant pressure. But here we're using the constraint for constant temperature, which is isothermal process. And if you include second law again, we've already actually mentioned this several times. This will give you a measure of maximum work. So during a reversible process, it means that we don't have irreversibility, and therefore the change of Helmholtz free energy will be minus W. And of course, if you reverse these two terms like A2, if you use over there, you have A2 minus A1 is minus W, but by multiply both sides by a minus sign, you have this. Or you can say maximum work. Okay, so this is what I just plotted out schematically. So the amount of work done by the system is maximum when you're dealing with a reversible process, and it will be equal to the decrease in the value of Helmholtz free energy. So originally in the final state and the difference of Helmholtz free energy will give you the maximum work that a system can do. And for an isothermal process conducted at constant volume, so now if we introduce another constraint, so at the beginning we only have one constraint, which is constant temperature. So imagine right now you have a different constraint, which means that the volume is also constant. So originally you have this, and if you also have constant volume, what will happen? So imagine that you are dealing with a system with just having the PDV work. Actually, for most cases that we're going to see in this chapter, they're only having the PDV work. If you have a constant pressure, constant volume process, it means that PDV is 0. Let's see. Constant volume here means that let's say dW is PDV, and this is 0 for the constant volume process, right? So in that case, the right-hand side of this one will be 0. Okay? It means that the Helmholtz free energy is a constant. But that is the case when you're dealing with reversible process. If you're dealing with irreversible process, you need to have this extra term being included. Okay? So it's the best if we go back to this term, this expression here. So A2 minus A1 plus this irreversible induced entropy change will be minus W. So if you're dealing with a constant volume process, then minus W will be 0. Okay, this will be 0. So you'll end up with this expression. And therefore, if you consider just a small change in terms of Helmholtz free energy or a small change in terms of entropy, this will be your final expression. dA plus TdS irreverse will be 0. But of course, if you're dealing with a reversible process, the expression will just be, let's say, T. If this is also 0 for a reversible process, then the final expression is just dA is 0. So for the irreversible process, which means that you have a spontaneous process, dA is less than 0. And for reversible process, dA will be exactly 0. Therefore, for any closed system, and the constraints are constant temperature and constant volume, dA is smaller or no greater than 0. So this is an important conclusion that dA is no greater than 0 at constant T and V. So when you have two independent variables fixed, typically you can extract dA being 0 if you're dealing with reversible process, and it will be smaller than 0 if you're dealing with irreversible process because you have dSIRR. Okay? So for any closed system, this is the case. And more importantly, this is closed system. Okay? I think for most of cases, we're dealing with closed systems. So we're not dealing with open system. We're not dealing with isolated because we need to have some heat exchange. Okay? So typically closed systems. And therefore, the Helmholtz free energy can only decrease or remain constant. And the equilibrium is attained or the equilibrium is reached when Helmholtz free energy achieves its minimum value. So if we look at this plot over here, we have a decrease of, say, Helmholtz free energy. And when the system is, for instance, is reaching this point, we know that at this point, for instance, dA is 0. And we know that this is the minimum value of Helmholtz free energy. Therefore, this is the equilibrium point. Okay? And spontaneous process means that it will go from higher Helmholtz free energy to lower Helmholtz free energy spontaneously. Therefore, you have this here. You have dA, less than 0. Because if this is a spontaneous process, it will just go spontaneously from state 1 to state 2. Okay. And again, an important feature for using Helmholtz free energy is that you're dealing with constant temperature and constant volume. Okay. Later we'll see that the reason why we have to introduce different kinds of free energy, later we'll see Gibbs free energy, is because if your system is going through a constant temperature and constant pressure process, so the constraints become constant T and constant P, then you have to use a different kinds of free energy. You'll use Gibbs free energy. But in the case of constant T and V, you're going to use Helmholtz. And interestingly, typically for physicists, they will use Helmholtz free energy for their calculations. But for chemists, typically you use Gibbs free energy because you are typically dealing with different kinds of systems. Okay, for physicists, typically you want to have the volume fixed, like I mentioned earlier, because when you're dealing with statistical mechanics or quantum systems, typically you want the volume to be fixed, such that the energy levels are fixed and you don't have to worry about the redistribution of the energy levels. So therefore, for physics, if you're going to take like statistical mechanics in the future, you'll see that you'll encounter Helmholtz free energy a lot, but you won't see a lot of discussion on Gibbs free energy. But since maybe some of you are more into the chemistry, then you will see a lot of Gibbs free energy. For instance, for the next semester of thermodynamics, I think the later half of this textbook, a lot of things are discussed in terms of Gibbs free energy instead of Helmholtz. Okay. So an example of discussing the usefulness of Helmholtz free energy is, of course, we have to find a system with constant temperature and constant volume. And in this case, for instance, we're looking at a system with solid phase and vapor phase. So in this case, we're not dealing with liquid and gas. We're dealing with solid and gas. Actually, there's no big difference, but I think the reason why the textbook used this kind of example is because it's much easier to do some calculation. Although I think in the new version of the textbook, it doesn't go through any detailed calculations. But I will show you some of my previous calculations later. So considering a solid vapor system, so you have the solid, let's consider maybe just like a maybe carbon dioxide. For instance, you have the evaporation or sublimation, from the solid CO2 to gas CO2. Okay, and they're all confined in the same box, and this box has a constant volume. So the total volume is V, and we know that because the mass, the total number of the particles is a fixed number. So Ns plus Mv is equal to N. So you have N atoms in total, and Ns stands for the atoms in the solid phase and Mv for the vapor phase. So this is fairly straightforward. And one thing that we want to find is the equilibrium vapor pressure, which means that we want to find how many particles will there be in the gas, in the vapor phase. Now, what will be the equilibrium number of vapor particles at a constant temperature? Because this system is in contact with a heat reservoir, so it's fixed at a certain temperature. And of course, intuitively thinking, you realize that when you raise the temperature, of course, there will be more and more particles going into the vapor phase, right? If you raise the temperature, of course, if you're dealing with dry ice, carbon dioxide, you'll know that there are more like gas coming out from the solid. So the vapor phase, the gaseous part, will become, you'll have more and more particles in the vapor phase. So we want to figure out what will be the number for that for instance, especially in the vapor part. So we start from the Helmholtz free energy because we're dealing with a constant temperature and constant volume system. And we know that the Helmholtz free energy is the internal energy minus temperature times the entropy. And in this case, we know that the temperature is fixed. The temperature is fixed. And if you change the number of particles in the vapor phase, then you'll change the total number or the total value of internal energy, because we know that the internal energy is proportional to the number of atoms in that phase, right? If you still remember, for the ideal gas, the internal energy is directly proportional to U is directly proportional to the number. So in this case, the expression of number is mv. So you can say this is, let's say, something like this. So it's proportional to the number of particles in the vapor phase, right? So that's the reason why this plot over here shows that the internal energy has a linear trend with respect to the volume, the number of particles in the vapor phase. For the entropy, it's a little bit more complicated, but we've already derived actually the expression of entropy for the ideal gas during the class before midterm exam, right? So we know how to express this, except that in this textbook there's no expression for that. But we've derived that before. There's something related to like log something, and if you know that maybe like KB log something, blah blah blah, and if you have a term that is related to log, you know that the expression will be something like, the trend will be something like this. The entropy, this is of course proportional to the number of the particle in the system, but it will gradually saturate, okay? And later I'll show you my own calculation based on what we derived before. Indeed, you'll see this kind of trend, okay, when you increase the number of particles in the vapor phase. So it means that here we're using MV, okay, and fixed volume, fixed temperature. And when you fix temperature, you fix U. So it means that the entropy only depends on the number of particles in the vapor phase, okay? And therefore, we know the expression of U, we know the expression of S. Now we can estimate the Helmholtz free energy by combining these two. So with a fixed temperature, we know that we just multiply the entropy term, this thing, with a constant number, constant T. But it has a minus sign. So the thing is flipped. The trend has been flipped. So originally, this is going upward, right? Here, it is going upward. But now, since you're having a negative sign, minus T, in front of it, so it's going down. And of course, the internal energy is still going upwards. Therefore, the Helmholtz free energy, A, is going downward at the beginning, and then it will just go up. So as a function of number of particles in the vapor phase, you'll see that there's a minimum over here. And that minimum represents the location that dA over dN, or dA over dmV equals 0. And if that's the case, then that's the equilibrium point. So as long as we can find, for instance, partial A, partial N is 0 and figure out what that MV is, then we know the equilibrium point. So we already know that we need to find this. And in this case, we're actually looking for this thing. Let's say this is constant temperature. And what else? The volume is also fixed, but I don't think we have to write that down. Maybe just constant temperature. This is 0. Then we can figure out like what MV is. So the first thing we do is, of course, A is U minus Ts. And we know U is a function of MV. And S is also a function of MV. So we can express A as a function of number of particles in the vapor phase. And then we perform this, to figure out what will be the equilibrium number in the vapor phase such that partial A, partial MV is 0. Right? So this is very simple calculus. But that's with an assumption that you know how to express this. Although schematically, you know that because so this is a function of MV, and this is, let's say this is U. This is, this is minus Ts. So if you combine these two, you know that there's a minimum here, and then it'll just go back up. So we want to know this point, and this corresponds to this relation because here the slope is 0, and we want to figure out what this is. But we need to know, this is A. But we need to know the exact expression of U and S as a function of particle number in order to calculate this analytically. Okay? But unfortunately, in the textbook, there's no such kind of derivation, so you'll only see this kind of figurative, I'll say, explanation. And in reality, you can do that. Let me show you that quickly. So we can do this. I use Mathematica to do calculation, and maybe it's hard to see. Okay, here. So imagine that you have a large number of particles, and I set up the, for instance, the Boltzmann constant, the Planck constant, and the volume is set to 1 for no reason. But there are some other factors that you need to consider because we want to calculate the entropy. So I've already shown you that the internal energy is very simple, but for the entropy part, we have to use the expression that we derived in class before the midterm exam. Okay, and if you do that, and remember this is having the Gibbs paradox correction term. And if I plot internal energy and also this entropy as a function of number of particles in the system in the vapor phase, you'll see exactly what the textbook plot. And this is very similar. So it's just to verify that the textbook is not lying to us. And of course, if you plot the Helmholtz free energy, you'll see exactly what the textbook is trying to say. Although you have to play with the numbers to make this kind of plot. And the reason why I have different curves is because I changed the number of temperature. The value of the temperature. So as you increase the temperature from 100 Kelvin to 400 Kelvin, you start to see that the equilibrium point shifted from here to here to here. It means that the number of the particles in the vapor phase has increased when you increase the temperature. And if you try to solve this minimum value, this point, using Mathematica, so you can solve that. So here is finding solution, and you use partial n is 0, and this is the solution that it will get. So as the number of a particle increases, you'll see that this is the increase of the temperature is increasing, the number of the particles also increasing in the vapor phase. Okay, so I think I'll stop over here and I'll come back to this later. So again, we want to solve this. We want to solve the equilibrium number of particles in the vapor phase. Therefore, we need to know the expression. So it is also very hard to solve by hands. So that's the reason why I use Mathematica, which is a software that allows you to do some simple symbolic programming. And you can just type in, although this is a paid software, so if you know Python, you can do this in Python using NumPy or SciPy. I think it should be very straightforward. And if we try to solve the equilibrium position, and we'll find that it is having this kind of exponential trend as a function of temperature. Okay, so for each temperature, you can solve for an equilibrium number, and then this number of vapor phase particle is further a function of temperature. Okay, so that's the reason why over here it states that the saturated vapor pressure is proportional to the concentration of atoms in the vapor phase. So this is the number of particles in the vapor phase in equilibrium at a certain temperature. And if we want to know the concentration, then it is this value divided by the volume of the vapor phase. And we know that this is the total volume, V, and this is the volume of the solid phase, so it's V minus Vs. And from the ideal gas law, we know that P is nKT over the volume of the gas. Okay? So this is a simple expression. And typically, actually, for the solid phase, the volume is much smaller than the vapor phase. So you can, for a good approximation, you can just use Vs approximately 0. Okay? And therefore, the pressure is approximately mv kT over the total volume. Okay? So here we have P is, let's say, T. This is the total volume. This is a solid phase volume. But Vs typically is much smaller than V. Because for the solid phase, the volume is much smaller than the vapor phase. So you can say the pressure is closely, let's say, over V, the total volume here. And therefore, this one is related to temperature, and here you also have the temperature dependence. And the paragraph here is trying to say that this pressure is related to the concentration of the atoms in the vapor phase. And the concentration is this term over here. So this is proportional to, let's say, this thing. Okay, because this is the number and this is the volume. So this is the concentration. And therefore, the pressure is not dependent on the volume in the system available for vapor phase. Typically, it is only related to the concentration. Okay, it's not related to the volume in the system available for the vapor phase. And therefore, typically, that's the reason why we typically state that the saturated vapor pressure is related to the concentration of the solution, right? If you remember from the high school chemistry, typically, if we want to calculate the saturated pressure, vapor pressure, we have to know the concentration of the solution. Okay, because concentration is more important than the actual number of particles and the available volume to contain those particles. It is the concentration that will determine the final saturated vapor pressure. And okay, so in the previous discussion, we know that this term, which is related to the entropy, will increase as the temperature goes up, which means that this thing will further goes down when you increase the temperature. That we already see that. So if that's the case, then you'll experience a lot. This will go down further and further while increasing the temperature. Right? If the temperature is going up, this curve will go down, and then the equilibrium number of particles in the vapor phase will increase. And so that's the reason why when I just show you in the Mathematica that there's an exponential growth of number of particles in the vapor phase when you increase the temperature. So this is what I just mentioned. And typically, that trend can be approximated by an exponential expression. Therefore, log P, the natural log of the vapor pressure, saturated vapor pressure, is related to the inverse of temperature plus some constant. So if you plot this out, you'll see that with only a very small change of temperature, there's a huge change of pressure. Okay, there's a huge change of pressure. And that's exactly what we saw in the derived form. So this is what we solved using the equilibrium number of particles in the vapor phase. And we'll see that there's an exponential growth. Okay, I plot this as the equilibrium pressure based on the ideal gas law. And this is the expression using what we just learned from the slide or from the textbook. And using this form, you'll see that there's also this exponential growth. Of course, this is originally is an exponential expression. So of course, you'll see that. But it is very similar to what we derived using the ideal gas law and using the Helmholtz free energy. Okay, so in short, although we didn't, even in the textbook, it doesn't try to verify how good or how well this fitting is between this one and this one. But let us just assume that for most of the cases, the vapor pressure will behave exponentially as a function of temperature. So when you increase the temperature by a little bit, there's a huge change of pressure. And the maximum temperature at which both solid and vapor phases occur is that temperature at which minimization of A occurs at MV is N. So there's a maximum temperature that you can go up to, there's a maximum temperature that you can go up to because once all the particles are in the vapor phase, then there's no further increase in terms of the vapor phase particles, right? So this cannot go like to infinity, right? The maximum of MV, let's say equilibrium, the maximum of this is simply the total number of particles in the system. So there is a maximum temperature that you can go up to. And beyond that, it won't further increase the number of particles in the vapor phase. So it's just textbook is just trying to state that using a little bit weirder way. But more interesting part is when you go down to 0 temperature. Okay, so from the opposite end, if you go down to 0 Kelvin, the entropy contribution to the Helmholtz free energy will vanish. Okay, so the minimization of A will coincide with the minimization of U. Therefore, there will be no particles in the vapor phase. There will be no particles in the vapor phase. So imagine that we're still using this expression or this plot to mimic the temperature change. If we go down to 0 temperature, then there's no Ts contribution. Therefore, the equilibrium position will be here at the 0 point, which means that there's no particles in the vapor phase, and all the particles will be in the solid phase. And that is consistent with our intuition, because when you go down to 0 Kelvin, there should be no kinetic energy for all these particles, so they should be all condensed into the solid phase. So this is just a simple example of how we use Helmholtz free energy to derive this equilibrium number of particles. So this is what we're trying to mention. But if you consider a different scenario, that at the beginning the system is in equilibrium, and you suddenly change the pressure. For instance, you can control a piston that is on top of it, or suddenly you can release the pressure by letting some gas out. If the vapor pressure is less than the saturated vapor pressure, then there's a spontaneous evaporation of the solid, right? Because if the pressure is suddenly becomes smaller, then spontaneously it should have some particles being evaporated or sublimated from the solid. And until the pressure is the same as the saturated pressure, the process will stop. So during this process, we know that for this either evaporation or sublimation, the system needs to absorb heat in order to evaporate some particles into the vapor phase. Therefore, you see that in this scenario, the heat reservoir holding at a constant T, but at the same time you can supply heat into the system. Okay, so we know that because this is an irreversible process. So although we supply a certain amount of heat into the system, but the entropy change for the particle system is actually greater than the heat supply. Right? We've already mentioned this several times. So although you have an increase of entropy due to the heat absorbed, like Q over T, but at the same time you also have this irreversibility entropy. So there are as IRR. So for the particle system, in fact, you have this extra term. So by combining these two together, again, this is exactly the same as what we mentioned in chapter 3, I think. You'll see that there's a small amount of irreversibility cost entropy for the combined system. And therefore, in this scenario, if it's an irreversible process, the change of Helmholtz free energy will be exactly the same as the change of irreversible entropy times the temperature. So at the very beginning of this class, we mentioned that the change of Helmholtz free energy is either 0 or less than 0, depending on the process. So delta A dA, or you can say delta A is less than or equal to 0. dA is 0 for reversible process, and dA is T times ds r for irreversible process, and this is minus, so this is less than 0, right? Okay. So for irreversible process, because you have this delta S irreversible, therefore your change of Helmholtz free energy will be less than 0. Okay, so in this scenario, even when you're dealing with a constant internal energy, constant volume case, you can still see the change of Helmholtz free energy because you have this extra contribution, right? If you don't remember, we can always go back to the very beginning that, of course, W is 0, and if you don't have delta SIR, delta A will be 0, but if you have T delta SIR, we know that delta A will be less than 0. It will be a negative term because you still have this spontaneity to minimize your Helmholtz free energy to a smaller value. Okay, so this is what I just mentioned right now. Okay. But in fact, I think for most of you in the next few months or even for next semester, Gibbs free energy is probably more important because for a lot of chemical processes and especially for material science, it's related to the Gibbs free energy, like how to derive your phase diagram. It depends on how to minimize your Gibbs free energy. So here we have to introduce that. We define Gibbs free energy as H minus Ts. So Gibbs free energy is defined as H minus Ts. So you have enthalpy, and we know that H is U plus PV. So you have something like this. So you have the internal energy plus the PV, P times V, and minus Ts. Okay. So if you're dealing with Helmholtz free energy, of course you only have U minus Ts. So you can also express this as let's say PV plus A. Sorry, I think more conventionally is A. Okay, it's the same thing. Okay, you're going to get the same thing. So for a system going through a change from state A to state 1 to state 2, based on first law, again, this is a similar derivation as what we went through for the Helmholtz free energy. We have all these three changes. We have the change of internal energy. We have the change of P times V. We also have the change for T times S. Okay, so for a closed system, we know that the change of internal energy here is Q minus W. It's the heat supply and the work done by the system. And therefore, G2 minus G1, and the change of Gibbs free energy before and after the processes is change of internal energy. We just bring this back down. And then we have these two extra terms. So now, for instance, when we talk about the Helmholtz free energy, when we have this kind of expression, we start to introduce our constraints, right? For instance, when we're dealing with Helmholtz free energy, we say this is an isothermal process. Then we start to do some math. And in this case, we have two constraints introduced here. We have temperature as a constant. Temperature as a constant, and also pressure as a constant. So temperature is a constant, and pressure is also constant. So it's isothermal and isobaric. Then the change of Gibbs free energy is actually, of course, a change of internal energy plus PDV. So this is the PDV work. And you also have this T delta S. Because when the temperature and pressure is fixed, P2 is the same as P1, and T2 is the same as T1. So you could bring these two terms out from the parenthesis. Therefore, you can have these kind of expression. if you have work that is beyond the PV work or other than the PV work, then the system performs, for instance, chemical or electrical work or magnetic work, then you coin that as W prime. So you call the work that is other than PV work W prime. Therefore, the total work is W prime plus the PV work. So in short, you can simplify the expression we just saw over here, by combining these two terms together, and then you are left with Q minus W prime over here. Okay, so let me write this, go through this again. So we know that, let me start from here, like G2 minus G1 is the heat involved minus the work, okay, the work done by the system. That's the pressure, and V2 minus V1, and the temperature term. And let's say the work, this is the total work done by the system. We know that it has some term that is related to, let's say, PDV. So this is the PDV work. Plus something else. Let's say, for instance, if you have a magnetic work, let's say magnetic or chemical work, and we call this W prime. Therefore, the work is just this PDV work plus any kinds of other work that can be found in the system. Actually, when we discuss the Helmholtz free energy, we assume that this is zero, right? We assume that for most cases we're dealing, for instance, just gas, then we don't have to worry about W prime. But in this case, I'm not sure why the textbook mentioned that there's possibility that you have this all other kinds of work, so will be introduced here. So if you plug this back in to the equation here, put this back in here. But of course, we know that this term will be canceled out with this. Therefore, G2 minus G1 is just Q, let's say, minus W prime, right? There's W prime, and then T, S2 minus S1. So you have this work that is other than the PV work, because we know that P delta V will be canceled out over here. But of course, if you're dealing with a case that without any chemical work or magnetic work or electrical work, then this term will be zero. So you will just have Q minus T delta S. Okay, then that's more straightforward. And again, when we recall the second law of thermodynamics, we know that T delta S is greater than Q or equal to Q. So if you plug, again, using this criterion, and you plug this back into here, here we have Q and minus T delta S. So eventually we'll have W prime is no greater than the change of Gibbs free energy. So this is similar to what we saw earlier for the Helmholtz free energy, right? Because for Helmholtz free energy, if you still remember, we have this similar thing that, let me go back. The work done by that, let's say this is minus W, is greater than A2 minus A1. Or we can times a minus sign here and something like this, right? If you multiply both sides by a minus sign, you have to flip the sign of inequality. So this is for the Helmholtz free energy. And for the Gibbs free energy, you have a very similar expression that the W prime is no greater than, let's say, G1 minus G2. Right, because there's a minus sign over there, so you can flip the sign for G1 minus G2. Okay, so again, if this chemical work, the work that is other than PV work is 0, okay, then you can have this expression. So you know G2 minus G1 plus T delta SIR should be 0. Okay, it should be 0. Or, you know, if there's no extra work other than PV work, we know that this should be 0. If that's the case, we know that G1 minus G2 should always be greater than 0. Okay, so that's the spirit here. No, that's the spirit here. So very similar to what we saw for the Helmholtz free energy, except that here we're dealing with isothermal and isobaric. But for the Helmholtz free energy case, we're dealing with, at the beginning, just isothermal, right? Just isothermal. So this equation, this indicates that a process can only occur spontaneously if the Gibbs free energy decreases. So that's the same as when we saw for Helmholtz free energy. Okay, there's only this spontaneous process when the Helmholtz free energy is decreasing. So if you have a reversible process such that delta S IRR is 0, then this is a criterion for thermodynamic equilibrium. And to reach that equilibrium, it is required that dG is 0. So delta G should be 0, which means that the Gibbs free energy should reach a minimum when the system is going to the equilibrium state. And especially when you're dealing with isothermal and isobaric process. So actually, I should highlight these two constraints. So when we're dealing with isothermal and isobaric process, constant T and constant P, then the criterion for judging if the system is at an equilibrium state is that dG is 0 or not. Okay, so if you're dealing with, for instance, isothermal and isovolume process, then we know that you have to use dA is 0, right? So that is the most important thing that you have to keep in mind. Like, what will be the time for you to use Helmholtz free energy, and what will be the time for you to use Gibbs free energy? So we know this earlier. So let us consider just reversible processes. We know dA is 0, dG is 0, and this is for constant T and V, and this is okay. So we need to clarify that what kind of process you're going through. Okay. So for isothermal, isobaric, you use the Gibbs free energy to judge the equilibrium. And for a system undergoing process at constant T and P, the Gibbs free energy can only decrease or remain constant. So in the reversible process, we know that the Gibbs free energy is always at 0. I mean, the change of Gibbs free energy will always be 0. And if you have a spontaneous process or irreversible process, it will decrease. Therefore, it's less than 0. Okay. So if you take the irreversible process also into account, then this will be So the criterion for dg is 0 for equilibrium is particularly useful. And it's practically useful for, I think, mostly chemists, and probably for you as well, for you in the material science. This is a more relevant free energy. Actually, at least for myself, I rarely use Gibbs free energy because I'm mostly studying in different fields. But I think for most of you, for the next couple of months and for next semester, you'll encounter Gibbs free energy a lot. So in fact, we can summarize all these relations together because they are very symmetric, and it's kind of beautiful because you have 4 different kinds of thermodynamic quantities: the internal energy, the enthalpy, the Helmholtz free energy, and Gibbs free energy, and they all can be expressed as how to say that, the perfect differential of 2 other kinds of independent variables. For instance, we've already seen that the internal energy depends on the entropy and the volume. Therefore, we express internal energy as a function of entropy and volume. And since the enthalpy is U plus PV, so dH can further be expressed as TdS plus VdP. And the derivation is fairly straightforward. Okay? You start from the definition, and you use this perfect differential. And dH is, of course, du plus d, this whole thing, PV. And we know from calculus that then you have 2 terms. You have PdV and you also have VdP. And then you use the first law of thermodynamics. We know that du is TdS minus PdV. So if you use that, you'll see that these 2 terms will cancel out. So this is a trick that we typically would use. And then you'll end up with TdS plus VdP. So similarly, if you do that for instance, Helmholtz free energy, I don't want to do that for Gibbs free energy. You can do that at home. But for Helmholtz free energy, is you go through the same thing. That the definition is something like this. Therefore, dA is so these are just math. So that's one good thing of chapter 5. Like if you don't know anything about thermodynamics, if you know calculus, you can still solve almost all the problems in chapter 5. And du, based on first law, we know that first law is something like this. So we know the expression for du. Du is TdS minus PV. And so this is fairly straightforward. You have these 2 terms cancel out. Okay. So you have these 2 terms. So we know that Helmholtz free energy is indeed a function of 2 independent variables, dV and dt. So recall that when we try to explain this equilibrium criterion, we know that Helmholtz free energy is suitable for constant temperature and constant volume processes. So if you don't know what will be the constraints for a certain free energy, you can always go through this, and then if you end up with dV and dt, then you know that for dA to be 0, you need dV and dt to be 0. So you have to go through constant temperature and constant volume process. And if you do the same for Gibbs free energy, of course, you will end up with dt and dP. So that's the reason why here you see that it is minus S dt plus VdP. Okay? And of course, to do that,
I won't go into details, but again start from the expression H minus Ts, and this is U plus PV minus Ts, and therefore dG has many terms. Actually, it's pretty straightforward. We can just use maybe du is, again, TdS minus PdV. So we know that, again, these two terms will cancel out. This will cancel with this one. So we end up with these two terms. This is actually pretty straightforward. So even if you don't memorize these things, you can derive like in several seconds during the, say, the second midterm exam. Yeah. Yeah, you should be able to derive these things. So it's very straightforward. So if you summarize all these together, you'll see all four very similar formats or very similar expressions. So du, function of S and V. dH is a function of S and P. Although we rarely use this one, we rarely use H as a function of S and P because we know that it's hard to, let's say, measure the change of entropy. So that's the reason why the same for this one. We rarely use ds as our measure. But these two are very common because we can fix temperature, we can change temperature, we can fix volume, we can change volume. And these are the things that we can control and measure. So that's the reason why we have to introduce Helmholtz free energy and Gibbs free energy, because those quantities are more relevant to the physical quantities or the independent variables that we can control and measure. Okay. So previously, what we mentioned, these are all like without the change of composition. For instance, just single phase, and there's no change in terms of the number of particles, and there's no works other than PV work. However, if you're dealing with variation of composition, or even the size of the system, for instance, there are particles coming in and out of the system, then you have to change your expression for the free energy, and also, for instance, even for the internal energy, you have to change the expression. So what we just saw earlier are only for the closed systems, and the closed system for fixed size and also fixed composition. Therefore, we only need two independent variables. So here, for instance, for Gibbs free energy, we only need pressure and temperature to tell us the change of Gibbs free energy, and for Helmholtz free energy, we only need the volume and the temperature. But in fact, if your composition is going to change for your system, then you need to introduce some other terms. And for instance, we know that the change of number of particles can be expressed as, for instance, dn. Then there must be something that is related to dn, has to be added to the original expression. So, for instance, if you're dealing with a chemical reaction, this is a very simple reaction, and the minimization of Gibbs free energy at constant pressure and temperature occurs when the system has a unique composition, right? This is based on, say, high school chemistry. Now you know the concentration, for these two and these two should have some certain, ratio in order to make sure that this reaction is at its equilibrium or dynamic equilibrium. So when that equilibrium is reached, the Gibbs free energy is minimized. But it also means that this Gibbs free energy will be affected by the concentration of all these chemicals. Okay, so the concentration or the composition of all these chemicals will change the Gibbs free energy. So again, Gibbs free energy is of course, here, a function of pressure and temperature. But even when you fix the pressure and temperature, there's some other variables that have to be considered. For instance, the numbers of particles, or in this case, the concentration of all these 4 chemicals. Right? So that will also have to be included to have an exact expression for Gibbs free energy. So that is the case when you are dealing with material systems with more than one species of chemicals. So therefore, Gibbs free energy is a function of course, temperature and pressure, and also the numbers of moles of all of the species present in the system. It is better to express Gibbs free energy as a function of temperature, pressure, but also the number of particles, or you can say the moles of particles for different species, and you have to add them all together. Therefore, the perfect differential of Gibbs free energy, dG, this term, should have this, and other terms that are related to all the species, chemical species in the system. And that's the reason why over here you see that you have, of course, partial G, partial T, partial G, partial P, but also partial G, partial Ni, and Nj, and et cetera, et cetera. So let me move this. We already know that here, from here, is but we need something that are related to, for instance, we have different, for instance, 3 different species of chemicals, and they are named I, J, and K. And how many moles of them are there in the system? So we have to add them up. But we also know that the expression for this is partial P. And in this case, temperature is fixed, and all the species are fixed. Right? And then we also have this partial differential against temperature. This is with fixed pressure and fixed the species. And then we also have these things. And typically they are expressed as, I sum them up together. Let's say you have IJK, blah, 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 and this is partial G. Or you can say it's I from 1 to some certain number if you have many of different species in your system, and D and I. And this is the case when P and T and let's say all these species are fixed, except the one that you are dealing with. Okay, let's say, for instance, something like this. When you're taking the differential against Ni, then Ni is a changing variable. So, but other compositions should be fixed. Okay, for instance, Nj, Nk, all the other things should be fixed. So this is the expression for the case when you have different chemicals species in your system. So we already know that, okay, so this is minus S. Will be the same as this one. And this will be V. Okay. So this is what the textbook mentioned. So partial G, partial T should be minus S, and partial G, partial P should be the volume of the system. Therefore, equation 5.13, this one, this thing, can be rewritten as a simple form. So if you just move these two things down here, oh, sorry, I should have a dt here. I should put that in as well. So if you just move these two things here, and then you'll have the simplest expression for that. So it means that originally we only have these two terms. But right now, since we have the composition change, we introduce this extra term to take that into account. So when the temperature and the pressures are fixed, but if you have composition change, that will also change the Gibbs free energy. And that change, the rate of change, is expressed as partial G, partial N. Okay? And for a certain species, Ni, it is partial G, partial Ni. And I think most of you have already seen this before in the chemistry class, that this is defined as the chemical potential, right, for a certain species. The partial G, partial Ni here, this term is simply mu I. It's simply mu I. And this is the chemical potential. Okay? So the chemical potential of a certain species, chemical potential. Of a certain species I is written as mu I, and it is expressed as partial G, partial Ni. So by changing a little bit amount of a mole of particle in the system of a certain species I, that will change the Gibbs free energy by a certain amount, and that rate of change is defined as the chemical potential of that certain species. So the chemical potential of I in a homogeneous phase is the rate of increase of Gibbs free energy with changing Ni. So when the species I is added to the system at constant T and P, and the numbers of moles of all of the other species, and typically we express the total change of Gibbs free energy as something like this. So this is the most simplified form. So you have minus SdT and VdP. That's from the macroscopic thermodynamics. But you also have the chemical species change. If you want to take that into account, then you have also this term. And if you're using the 6th edition of the textbook, I think it also has this magnetic work. So you'll see 3 terms in front of the chemical potential term, and then the chemical potential term as well. But I think it's better than for us to just ignore the magnetic work at this point, because then the expression is more symmetric. It's more beautiful in this way. So in my opinion, of course you can memorize this, but like I mentioned earlier, these are very simple to derive. And for the last term, you only need to memorize that if you have chemical change or composition change, you have to add this extra term, depending on how many species of chemicals you have in your system. And an interesting note is that this equation can be applied to open systems. So you can have like an open system, which means that you can have matter exchange. The particles can come in and you can come out, can leave the system as well. And as well as heat with their surroundings. So basically, you can discuss an open system that you can exchange heat and also particles with outside. And therefore, the composition change will also be taken into account with these. And if you use the same procedure, like I just mentioned earlier over here, you'll see that for du, again, you have these first two terms, but then you also have the change of internal energy with respect to the change of chemical species. Okay, so you have partial U, partial Ni, which corresponds to partial G, partial Ni here. And you also have the partial H, partial Ni. And of course, for Helmholtz free energy, you also have the same thing. And it turns out that all these things are the same. So we'll go through this later, but in the end, we'll reach a conclusion that this chemical potential, although defined as partial G, partial Ni, it is the same as partial U, partial Ni. So it does not really matter which chemical potential, which thermodynamic potential you use in the first place. If you're using internal energy, if you're using Helmholtz free energy, as long as you take the partial derivative against that certain chemical species number, or the mole number, you get the chemical potential of that certain species. So we'll come back to this derivation later. So we mentioned that the chemical potential seems to be the same for all different kinds of thermodynamic quantities like U, H, these all auxiliary functions. If you're using U, then the chemical potential part is partial U, partial Ni. And for H, then it's naturally this expression. If you're using Helmholtz free energy, of course, it's partial A, partial M. And since Gibbs free energy is H minus Ts, or U plus PV minus Ts, if you do the derivation, you again, like what I just went through over here, eventually you will have these terms. And du, of course, if you're using the same thing, if you're using this expression and to plug in, you'll realize that after you cancel these terms out, like what I did over here, you're left with the original minus SDT plus VDP and this extra term. Okay? So we suddenly realize that this extra term should be the same for all different auxiliary functions. Either you're using U, you're using enthalpy H, you're using Helmholtz free energy. For instance, here is partial U, partial Ni. But we know that if we start from directly start from dg, or partial G, partial N, this will be partial G, partial N. So it means that all these four should be the same. All these four should be the same, and they are all chemical potential defined as mu I. Okay? So this helps us simplify the original formulas to express du, dh, da, and dg into these four expressions. And they are fairly straightforward. You have the original two terms with an extra addition of chemical potential. Okay, so these are very straightforward. And therefore, if you want to use words to describe them, the internal energy is the characteristic function of entropy, volume, and composition. And enthalpy is that for entropy and pressure. And we know Helmholtz free energy and Gibbs free energy already. So the equation is called the fundamental equation, especially for the Gibbs free energy. The reason why we call this fundamental because due to its practical usefulness, especially for chemistry people. And the dg is minus ddt plus vdp, of course, plusing this extra chemical potential term. And the comparison of this equation is this to the first law. to the first law will give us that the delta Q is, of course, correlated to TdS, but the work, delta W here, is actually related to, first of all, PDV, so it's very natural that we have the PDV work, and then we have the chemical work. So this corresponds to what I mentioned earlier, that if you're just dealing with, for instance, gas, and you are not dealing with any chemical reaction or any electrical work, then all the work that you have to worry about will be PDV. But if you're dealing with systems with, for instance, chemical composition change, for instance, a chemical reaction, then the work should have this extra term. So this corresponds to the W prime that we mentioned earlier today, right? When we talk about Gibbs free energy, we say that this W is PV2 minus V1 plus W prime. And this work is the work other than the PV work. And in this case, if you're having chemical change, composition change, this will correspond to the chemical work done by the system. So therefore, previously denoted as W prime. So the total work is the sum of PV work and the chemical work. Okay? If you're dealing with an open system and if you're dealing with a chemical reaction. So right now we're going to go through some maths. So let us start from the very first expression for the internal energy. Du is TdS minus PDV plus this chemical expression, chemical work. And we know that, therefore, the internal energy is a function of S and V. Here, S and V and N. And so here we only have one, like Ni, but it means that you, for instance, if you have three different chemicals in your system, then you have N1, N2, and N3, right? Three different species, and they have three different possible numbers. Therefore, if you express the perfect differential as its original form, we already know that the partial S, partial V. For the first two terms, I've already mentioned that before. Or if you're dealing with Gibbs free energy, we know that, for instance, partial G, partial P at constant temperature is volume, right? But here we're dealing with internal energy, so we know that T is partial U, partial S with fixed volume and fixed species composition, and the pressure will be partial U, partial V with fixed S and fixed composition. It's no big deal. And if you do the same for enthalpy and for Gibbs free energy and for Helmholtz free energy, this will yield these four relations. Okay, so the temperature, again, is partial U, partial S, but it's also partial H, partial S. If you don't know why, of course, we can go through that, but it should be pretty straightforward. So I'll just do one here. So for instance, let us start from H. And dH is and from the first law, we know that this is du is this. Therefore, these two terms cancel out, so it's TdS plus VdP. And we also know that dH is this is at constant pressure, and this is at constant entropy, right? Therefore, you can say temperature is partial H, partial S at fixed pressure, and also volume is partial H, partial P at constant S. Is there any? Yeah, over there. So we have derive this and also this one. Okay? So imagine that each expression will contribute two formulas. So in the end, you have eight of them over here. And there are some tricks that allows you to memorize these more easily. I have a video on that. You can go through that on the Seba. I uploaded that online at the very beginning of this semester. And that will help you, quickly derive all these things. So Maxwell relations is some further mathematical tricks based on what we already derived. Okay? So imagine that if some certain function is a state function and it's a function of x and y, so you have two independent variables, and it is a closed system and with fixed composition, so we don't have to worry about the chemical work and the chemical composition. And let us express this state function as a function of x and y, so z x, y. Or similarly, for instance, if you're dealing with h, h is function s and p, something like that. And dz is, of course, partial z, partial x, partial z, partial y, and you have with the dx and dy. So if the partial derivative, the first one, is itself a function of x and y, say partial z, partial x with fixed y is, let us call that L, and it's also a function of x and y. And similarly, let us say this second term, this partial differential is also a function of x and y. Then this dz is something like this. And we know that since this is a perfect differential, therefore, if we take further derivative of this partial z, partial x, which is denoted as, I think, L, if you take partial L, partial y, it will be the same as partial and partial x because z is a perfect differential. I think we did the same thing in the first chapter, right? So this is a restatement of what we already know. So if we have, again, these expressions, and if we go through this kind of derivation, we'll end up with these four expressions. So the partial t, partial v at a fixed s is the same as partial e, partial s at fixed v. And so you have four of them because you have four different expressions for those auxiliary functions. And more importantly, for instance, if you're dealing with partial s, partial v at a fixed t, or partial s, partial p, fixed t, and if you're dealing with these kind of expression, because we don't know the entropy change, and it's hard to measure the change of entropy, but we can derive that, from the change of volume as a function of a temperature. So, for instance, if you can measure the change of volume as a function of a temperature, then from that you can derive, or you can estimate the change of entropy, as a function of pressure. And these tricks, these mathematical tricks will allow us to replace some terms that is not desirable, for the experiments, and to replace them with some other variables that can be measured. So you can estimate, for instance, the change of entropy of the system, or the change of, I think mostly it's the change of entropy, because for all these things, pressure and temperature and volume, these things can be measured and fixed, but it's really hard to control or measure entropy. So in order to estimate entropy, we typically will refer to these expressions, which allows us to simplify the problem. And if you don't know how to derive this, we can, of course, pick one to check. For instance, which one we should, maybe we can use this one. So right now we have, let me rewrite this. Let's say, here we have dH is TdS plus VdP. And we also know that this is therefore, we know that this is, if we do this, this will be the same as fix P, right? These two will be the same. Because in the end, these will just be and for left-hand side and right-hand side, these two are the same. Because dH is a perfect differential. So we can do this. And we already know that this is temperature, and this term over here is volume. Therefore, we have partial T, partial P at a fixed entropy will be the same as partial volume, partial S at fixed pressure. So this is one of the Maxwell relations, as we will see over here, the second one, because this is from the enthalpy, so it's listed as the second one. So if you use the Helmholtz free energy expression, you should be able to get this one. If you use Gibbs free energy, you should be able to get this one. Okay, and although it seems to be having no certain rules, but if you go through the videos that I posted, there's some certain trick that allows you to memorize this in a very fast way. But I don't think you have to memorize these things, because I will provide these things, Maxwell relations, these four, during the exam. So of course, if you want to memorize this, be my guest. But I think it is more important to figure out how we derive these things. Okay. So these are the previous four formulas that we saw are called the Maxwell's relations. So these are not the same as Maxwell's equations, because we know Maxwell's equations are for electromagnetism. So you can say these are the Maxwell's relations for thermodynamics or for thermodynamic quantities. And those contains many experimentally measurable quantities. For instance, temperature, volume, pressure, except for entropy. Entropy is hard to measure experimentally. But we know that entropy is expressed as a function of temperature and volume for ideal gas. We've derived this before, and therefore ds can be expressed as something like that. You have partial S, partial T, and also partial S, partial V. And for a reversible process conducted at constant volume, we know that TdS is delta QV, which means that there's no PDV work, and because this is constant volume, and therefore du is CV dt, or n times m, depending on the size of your system. So it's n CV dt. Therefore, the first term over here, actually we've already seen this before, is n times CV over t. Okay, so we know from the first law, we know that this partial S, partial T, this first term is actually n times CV over T. Okay, and the equation 5.33, it's I think this one, the box one. If you use this relation, then you can replace this seems to be hard to calculate term into something that we can handle. This is something that we can deal with, because we know for ideal gas, there's a certain relation between the pressure and the temperature, right? So if you don't know the exact form of entropy as a function of volume, then if you use this trick, mathematical trick, then that will give you this much easier relation such that you can calculate. So the bottom line is that the second term is hard to calculate, but if we have the trick or one of the Maxwell relations, the third one over here, we can replace this term by partial p partial t. Then ds can be expressed like this. So this is much easier for us to calculate. And for ideal gas, like I mentioned earlier, it's having this ideal gas law. So partial p partial t is fairly straightforward. It's just nr over v. And therefore, ds of the ideal gas is simply these two terms. So of course, they are both like proportional to n because we know that entropy is proportional to the number of particles for the ideal gas. And the first term is coming from the internal energy part. So it's related to CV dt. But since we're calculating the change of entropy, we divided that by temperature. And for the second part, it's actually originally partial S partial V. But in this case, we don't know what partial S partial V is, so we replace that by using Maxwell's relation. And then from that, we know that it's simply nr over V. And if you do the integration, from state 1 to state 2 to calculate delta S, because this is integration of dt over 1 over t, so you'll have a log term here, and you also have a log term over here. So it's simply ncv log t2 over t1 and nr log v2 over v1. So eventually, for this reversible process, if you have an isentropic process, for instance, if you're dealing with there's no change of entropy such that delta S is 0, then you have this expression. You end up with these two terms adding up and should be 0. Then you retrieve the original expression or the relation for the ideal gas, right? The PV gamma to the gamma should be a constant. So this is another way to derive that expression. Remember, for the adiabatic process, we know that dq is 0, therefore TdS should also be 0 as well. So in that case, the ideal gas, before and after the process for state 1 and state 2, they should follow this rule, right? Or you can say P1 and if you start from the perfect differential of entropy and you go through the derivation, and later on you set the delta S to be 0, you will arrive at exactly the same expression. Okay, you just need to do some tricks for T2 and T1. Replace that with P and V, and therefore you'll get the same expression for the adiabatic process. So for this example, again, to summarize this, it's just the logic behind this is that we know that this entropy, let's say, if we want to express this as a function of temperature and volume, and therefore we know that ds is fixed volume and partial S partial V at a fixed temperature. And we already know how to write this from the definition of let's say TdS is something like this, right? This is from the first law and the second law. and if it's a constant pressure process with fixed V, so we don't have to worry about dV part. Therefore, you know that partial S, partial T, this is NCV dt. Then partial S, partial T is simply T over NCV. Okay, so the first term seems to be a little bit more complicated, but it is originating from the first law and the second law. Okay, and therefore this is related to the change of internal energy part. And the second part is related to the change of volume, but we don't know the expression for partial S and partial V. I mean, we don't know how to do that. And so from the Maxwell's relations, we replace this to partial P, partial T. And in fact, if you do that, this is much easier to calculate because we know from ideal gas law, this is simply N times R. Sorry, there's a V over here. Yeah, I know that I missed something. Yeah, so if you do the integration to figure out delta S, this will be what you get. So this is one of the example that I don't think it's that important, but it sort of shows you like what the philosophy of introducing all these expressions are, because in many calculations, for instance, you will end up with something like partial P, partial S, and you don't know how to calculate that. So it's good that, for instance, you can replace that with partial T, partial V, and then you can do some calculation. But the reason why I boxed these two is because these two are more frequently used. Because if you look at the right-hand side, they are all P and T and V, and all these three are the variables that you can measure and control. So that's the reason why I boxed these two, because these two are more frequently used. Okay. So let us look at another example. So for a closed system, again for fixed composition, so we don't have to worry about chemical work, chemical composition. We know that du is TdS minus PdV. So let us look at partial U, partial V. And the reason why we want to look at this is because, let us look at the conclusion. We want to prove that partial U, partial V at a fixed temperature is 0. In fact, we've seen this before, right? When we go through the statistical mechanics, and I think also in the midterm exam, right? We have this problem, and in fact, this is identical to, I think, to the things that we will see in the midterm. We saw in the midterm exam that we start from here, partial U, partial V, the fixed temperature. We want to see this is 0, but the last term seems to be pretty straightforward. It's just minus P. But the first term is a little bit complicated because you have partial S, partial V. And again, we don't know what this is. So if you have this term, remember, if you want to calculate, just replace that with partial P, partial T at a fixed volume. So using the Maxwell relation. Okay? And if you do that, then the expression will be pretty straightforward. And if you're dealing with ideal gas, again, this term will be nR over V times T. And you know that nRT over V will just be pressure, right? So pressure minus pressure will be 0. So if you use Maxwell relations, and the problem that you went through for the midterm exam will be very straightforward. You'll end up with just partial U, partial V at a fixed temperature becoming 0. Okay. So the internal energy of an ideal gas is independent of the volume of the gas. So this is by using some mathematical tricks, which allows you to derive this in a faster way. But for closed system, again, with fixed composition, if we're starting from dH, let us look at the enthalpy. And for the enthalpy, in this case, we want to check partial H, partial P. So in fact, we can check a lot of different things. For instance, if I want to check like the change of enthalpy with respect to volume, I can also use partial H, partial V at a fixed temperature. But in this case, in this example, in the textbook, it asks us to look at partial H, partial P. And similar to what we saw earlier, there must be a reason for that. So partial H, partial P at a fixed temperature is something like this, because we have the expression over here. And again, this is hard to calculate, right? Because we don't know the change of entropy as a function of pressure. So in order to do that, we use, again, the Maxwell relation, one of the Maxwell relations over here. The second one that we haven't used that yet. So it's minus partial V, partial T. So if we plug in, again, you'll see that eventually for ideal gas, this term is 0. So for ideal gas, partial H, partial P at a constant temperature is 0. So we have these two conclusions, from the Maxwell relations. So for ideal gas, we already know that the volume change at a constant temperature will cause no change in terms of internal energy. And now we also know that partial H, partial P at what? The constant temperature is also 0. So these are two important features for ideal gas. Although we already know this from the very beginning of this semester, we use several different ways to derive that, including the ones you went through in your midterm exam. But this one is new. We know that for enthalpy change in terms of pressure, it should be 0 at a constant temperature for the ideal gas. So the conclusion here is that the enthalpy of the ideal gas is independent of its pressure. Okay. And there are several useful relations besides the Maxwell relations. So I recommend you to, you don't have to memorize this because I will provide them in the midterm exam. But again, please remember how to derive, or at least understand how to derive these things. But another useful expression, actually very useful expression, is called the upstairs, downstairs, inside out formula. And the starting point is, again, the perfect differential. We'll always start from here. And imagine that there's no change in terms of dx. So let's say dx is 0, which means that it's a fixed x condition. Then if dx is 0, we know that these two things add up to be 0, so they're having this negative sign if you move one of them to the other side. And more importantly, this expression over here only will sustain when x is a constant, which means that dx is 0. Okay? If you further move them to one side, you'll arrive at this expression. So partial x, partial y, partial z, partial x, with fixed z, x, y is minus 1. So a lot of people will misuse this expression by taking this as unity, as a positive one. But in fact, this should be minus 1. And the reason is because the derivation starts from this point, and you set this dx to be 0, so you always have this minus sign here. And if you further take the derivative, like partial x, partial z over here, there's this minus sign that you have to consider. So if you move this to the left-hand side, you'll end up with -1 here. So it's not 1. So it's not like so it's not like just canceling like all these things out and then there will be 1. In fact, you have to remember that you have the constraints over here. Therefore, this is -1. So this is a very useful relations because, for instance, let's say if you have something like this. So if you have this one, like for instance, if you have this one and this one, and if you want to calculate partial t, partial v, you can just use these two products and then times -1, right? So it helps us to quickly calculate one of the partial differentials, as long as you know the other two. So this is a very useful trick that we will see. I think another good example will be we will encounter is in chapter 6 or chapter 7. And it's pretty complicated if you go through the normal process. But if you know this trick, you can solve the problem with a snap. So it's good to know some more math. So this is, I think we almost finished chapter 5, which is good. So because these are just maths, so it should be pretty straightforward. And so the corresponding relationship between G and H, we have Gibbs free energy, we have enthalpy, and we know that there's a close connection between Gibbs free energy and enthalpy because from the very beginning of the definition, we use H minus Ts. So Gibbs free energy, if you take a partial differential against temperature at a fixed pressure, it will just be minus S. We've already seen this before from this expression. And at a constant pressure and composition, so we don't have to worry about the chemical potential part, which means that we don't have to worry about the last term over here. We know that G is H plus T times this. The reason why is because the definition of Gibbs free energy is H minus Ts, and we know that S is partial G, partial T with a minus sign. So if you plug that back into the original definition, you will have a term like this. Okay, and if you time both sides with dt, and if you consider this as a constant pressure process, again, constant pressure, a constant composition, you will have g dt as h dt plus t dg, because you simply move this dt up to here and here. But please bear in mind that this is a constant pressure process, so P is fixed. Okay? And here you go through another mathematical trick that you divide both sides by t squared. If you do that, this is the left-hand side is simply this, and the right-hand side will be something like this. Okay? So if you further simplify that, you know that the differentiation of x over y is exactly the same. The reason why we simplify this as something like this is because we want to use this to simplify the expression. But the bottom line is that you end up with the expression of this Gibbs free energy and enthalpy as a function of temperature. So at this point, this seems to be not very useful, but the reason why we introduce this is because this Gibbs-Helmholtz equation is very useful for a closed system with fixed composition at constant pressure, such that you can calculate the change of Gibbs free energy by measuring the enthalpy at some certain temperature. Okay, so if you measure, for instance, at some certain temperature, the enthalpy, of the system, then you can know the change of Gibbs free energy at that certain temperature. Or in reverse, if you know some information regarding the Gibbs free energy, you can use that to calculate the enthalpy at that point. So if you don't have any, problems to guide you through, maybe this is not very useful at this point. But this is a very useful, a mathematical trick allows you to simplify the problem that you're going to solve. If you're still don't know like what I just mentioned, I'll go back again. So the reason why we write this down like this is having some certain reason. First of all, we start from here, and then we can derive something like this. There should be no problem. And then we divide both sides by t squared. Okay, and then we move some terms to the opposite side of the equation. For instance, here TDG is originally here, and we move that. For instance, we move this to this side, or you can say we move this to that side. So you have a minus GDT here, and it is originally HDT, but we have a minus sign because move this here, and then we divide both sides by t squared, so you have this expression. So you can check this by yourself. This is the same as this one. And the reason why we write this term like this is because we know that if we write the differential like this, this can be expressed as the differentiation of G over T, okay, due to the basics of calculus. So it turns out that G over T, if you take that derivative against temperature, you will have minus h over t squared. So the Gibbs-Helmholtz equation for the first one is that G over T dt is minus h t squared. Should be something like this. And if you do the same thing for Helmholtz free energy, from the symmetry, you can guess that this will be minus u over t squared. So these two are parallel to each other. And if you go through the same derivation process, you'll end up with this expression. Okay, so this is Gibbs-Helmholtz equation. So therefore, for an isobaric change of state for a closed system of fixed composition against constant pressure, and this is for constant pressure and composition is fixed, then you have this expression. And more importantly, if you put delta in front of it, the change, because we know that it's hard to determine the absolute value for Gibbs free energy and for enthalpy, but we can definitely measure the change, right? Because, for instance, during the combustion, if you burn something and if you have a chemical reaction, you can estimate the heat release or being absorbed by the system, and then you can estimate delta H, the enthalpy change. And from that, you can estimate the change of Gibbs free energy. So the heat of fusion, for instance, your system is going through a fusion process. The delta H can be obtained from a measurement of the variation of delta G, which is the free energy change of the reaction. And you have to do this with different temperatures. You have to measure, the change of enthalpy or the change of Gibbs free energy as a function of temperature. So in order to map this out, you have to figure out the change of Gibbs free energy at different temperatures. Okay. And delta G can be determined by knowing delta H. So in reverse, if you know the change of delta H at different temperatures, you can also calculate that change of Gibbs free energy. So this is the expression that links delta H and delta G. And so for experimentalists, if you want to really do the experiment and figure out the change of Gibbs free energy, you can just heat it up and measure, for instance, the change or the absorption of heat during the process, and then you can estimate the change of Gibbs free energy. Okay? And if you do the same thing for Helmholtz free energy and internal energy, you'll end up with a similar expression that I just wrote down. But of course, in this case, you are dealing with what? Still remember, this is for constant volume. And of course, composition has also to be fixed in order to use this one. Otherwise, you have to take the chemical potential into account. But when we use this Gibbs-Helmholtz equation or Gibbs-Helmholtz formula, we're not considering the chemical composition change. Okay, so please bear in mind these two things are very frequently used, I think, for the problems. So again, this is only applicable to closed system or fixed composition, and especially for constant volume. So depending on what kind of processes that you're going through, again, please bear in mind that for constant volume, you use the Helmholtz free energy and internal energy. And if you are dealing with constant pressure, you use the enthalpy and the Gibbs free energy. Okay. So here's an example. I think this is a very interesting example to use all these relations together to solve some problem. So imagine that you want to calculate, again, this seems to be very simple quantity, like Cp minus Cv. We know that for ideal gas, this is R, right? This is the gas constant R. But for all kinds of materials, we know the general expression is something like this. We derived this before, I think in chapter 2. In chapter 2, we have this expression before. And therefore, you have two terms. And we know that for ideal gas, in the end, this is 0, right? We just went through that again earlier. So because this is minus P, so in the end, this is 0. This term is 0. So you have 0 over here, and in the end, you have partial V, partial T is R over P. So this will be just R. But in this case, if this is not 0, then you have to worry about what's the final expression for Cp minus Cv. And first of all, if you want to solve that, this is not a very intuitive approach, but in the end, you'll get the correct answer, a very good and simplified answer. And we start from further complicating this one. The pressure, let us use the partial A, partial V as our expression for pressure. And the reason why we can do that is because if you go far back here, so you have this. And this might not be a very good expression because it's fixed S. This is not something that we can really control. So in order to further complicate this term, we use this one instead. We use partial A, partial V, and it's a fixed temperature. Okay, so if we do that, we have this term over here. We have a minus sign, of course, and the other things are kept the same. So we know that the Helmholtz free energy is U minus Ts. So you started to see why we introduced this thing. Because for the first term, it will cancel out with the second term. If this is U minus Ts, then we know that we will naturally have a partial U, partial V at a fixed temperature. And that will be canceled out with this term. Right? So we don't have to worry about this anymore. So here we have this term and also this term. But these two will cancel out. So this is the original, this is the original partial V. And this is from the Helmholtz free energy U. But these two will cancel out. So in the end, you have something like this. Again, we don't know how to deal with partial S, partial V, so we further use this expression. We already used that before, partial P, partial T. And if we plug in, this will be our final expression, not the final, the intermediate expression for that. And the last thing is the magical part. We use the upstairs, downstairs, inside out formula here. Sorry for that. We use this one that I just wrote down, which is fairly useful. Then we know that the above expression is simply just the product of those three. And these things are fairly straightforward because the first part is the expansion coefficient, right? It is the temperature dependence of the volume change. So it's the thermal expansion coefficient. Although there's a V over here, we can times that to be V alpha. So the second term is related to the compressibility. The compressibility is defined as beta. This is also shown in, I think, chapter 2, at the very beginning of this book. So it is the compressibility of the material. So in the end, you'll have the expression like this. You can simplify this into a very simple form. It's V times T, and you have alpha squared and over beta. And all these things can be measured experimentally, right? You can fix your volume, you can measure the volume, you can control the temperature, and more importantly, these are all these are all quantities that can be determined experimentally. Okay, so this is an example of how we determine some quantities by using the relations that we just learned. So next we will go through some examples, and then we'll have homeworks next time. Okay, so I'll stop over here.